So welcome to everyone who's joined us today live for our Calculus Part 2 lesson. As usual, I'm Dr. Rathilal and I'm going to be teaching you a few tips and tricks to help guide you through these sections. So today's lesson is made possible by NITX and the Mathematical Structures Research Group, as well as Absolute X. So what I'm going to do to begin is I'm going to recap on what we had done in Calculus Part 1, and then we're going to build on whatever we have learned. So just to note, I will be asking you questions frequently. So like always, for the frequent students, please note that I would like for you to respond to me in the chat box, and I will check the chat box frequently. All right, so last week, we had learned about differentiation from first principles, as well as a few basic rules of differentiation. So we had seen that the derivative of a function, which was f prime, right, so this is it, actually represents the slope or the gradient of the function f at a point x, and we denoted that by f prime of x. And the first principles definition, as we had gone through in that previous lesson, is equal to the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. So this is what we had seen, right? So that's what we had learned. From that point onwards, we had gone through a few examples where we had been given a function f of x and we were required to find the derivative of f of x, meaning we needed to find f prime of x using the first principles formula. And that meant that we needed to evaluate limits. Okay, so that's what we had reviewed. So this was another example from a past paper, which in particular was question 8.1 from the 2021 paper. I think it was the June paper, where we were given that f of x was 3x squared and we computed the derivative. So all of this is in the video that's already available to you on YouTube. We saw that that answer was 6x. Now moving on, we then summarized what we had done we summarized it as a few basic rules of differentiation. So the first rule that we had encountered said that the derivative of a constant is equal to 0. And in particular, for this case, we had seen from first principles that that is indeed true. So we let f of x equals to c, where c was a constant, and we computed the derivative of f, and we saw that the derivative of a constant is 0. The second rule that we had encountered was the power rule. And here, the power rule tells you something quite important. It says that whenever you have your variable raised to the power n, then the derivative of a function in that form is simply equal to the power n multiplied to the variable raised to the power n minus 1. So this was important. And then we went on to look at a few examples. But what I want to do is, I want to make this a bit more concrete, and I want to add 2 more rules in here for you. Right? And this will perhaps help you understand the examples that we answered a bit better. Okay, so the next rule that I want to look at is called sum indifference. And what this rule says is the following, that if f of x equals to, so I'm going to say that it's equal to the sum of 2 functions. I'm going to call it h of x plus g of x. So our function f is equal to the sum of 2 other functions. You take 2 functions and you add them together. All right. Then f prime of x is simply equal to the sum of the derivatives of those functions. Okay, so that's what this rule tells us. And of course, we can verify this using first principles. Now, similarly, we could replace this by a minus sign. So if the function was the difference of two functions, if it was h minus g, then the derivative of f would be the derivative of h minus the derivative of g. And that's what that rule tells us. So for example, if you were given that y equals to 2x squared, okay, rather, yeah, 2x squared plus, let's go with 7x, then would you agree that this could be regarded as the sum of two functions, where the first function is 2x squared and the second function is 7x. So if I wanted to compute the derivative of y, if I wanted y prime, then I would simply find the derivative of the first function, and by the rule, I will add it to the derivative of the second function. Is that clear? So although it was not stated last week, we did actually utilize this rule. And so because we did that, I thought it would be quite necessary for us to concretely write this down so that when you are revising, you know, well, this is truly possible. Does this make sense? I just want to get an idea from everyone. Has everyone followed what I've said? So we haven't calculated this derivative, but do we understand the reasoning that I've just given you, the rule that I've just stated? Great. So now to quickly sum up, let's write down the answer to this. So y is equal to 2x squared plus 7x, and I want y prime. What is the derivative of 2x squared? It would be 2 multiplied to the derivative of x squared. Utilize the power rule. What have you gotten? Do you agree that it is 2x, where x is raised to the power 1? And then what is the derivative of 7x? That is merely positive 7. Does everybody agree with that? And then, so as the answers come in the chat box, I'm just going to summarize this. This is merely 4x plus 7. Okay, so let's take a look at our chat box. Great, so it seems that we're all following. So that was just to wrap up those rules that we had, okay? And technically, we used another rule in here that is usually not stated in the content that you're learning in school, but this is simply telling you, and you will always find that this is true, that when you have a constant times a function, so maybe we could do this, right? Let's do this. Let me move this down. So I can say a constant times or multiplied to a function. So if we have that f of x is equals to a constant times a function g of x, then we have seen, or you have been using this rule without having known that it is always true. It is true that the derivative of a constant times a function is simply the constant times the derivative of the function. So for example, as we had seen earlier, so if I give you y equals, let's say minus 1 times x to the power 20. This is a constant times a function. Would you agree? Right? And if you do, then you would see that following this rule, the derivative of y is merely the constant times the derivative of that function. What is the derivative of this function, x to the power 20? It is merely 20 times x raised to the power 20 minus 1, which is 19. And so this is negative 20 times x raised to the power positive 19. Are we happy with that? Has everybody followed? Great stuff. Okay, so we've got some thumbs up. So This you could regard as your rule 3. So you've been utilizing this rule all along. And sum and difference you can regard as your rule 4. And then you can see that in here we have utilized constant times a function to get out this answer of 4x. And we have then used sum and difference because we've got the sum of 2 functions. And so when we computed the derivative, it was simply the sum of the derivative of this function added to the derivative of that function. And that's how we got 4x plus 7. Okay. All right, so we have another question in here. Okay, so this has nothing to do with the lesson itself. So I'm just going to move on. It's about the software. Eric, I can chat to you about the software and how to do this. Certainly, you can drop me an email and I'm happy to talk to you about it. Okay, so now that we've gone through these basic rules, so I had gone through one question with you last week, and then we ran out of time and I gave you a question as homework, didn't I? So let's answer that question together. What was the homework question? This was it. Okay, so this was the homework question. So let's see if I can. Okay, so got the homework question. All right, so this is what we want to answer. And this was question, if I'm not mistaken, from the paper, it was question, it's not scrolling, let me scroll down on my own. It's question 8.2.2. Okay, so okay, so let's attempt this question together. And so what it says is that we want to find g prime of x. Apologies, it skipped a few pages. Okay, here we are. We want to find g prime of x is if g of x is equal to the following. So looking at what we have, I've just given you 4 basic rules. Do any of the basic rules apply immediately to this? Essentially, what we have in here is we have the product of 2 functions, right? You can regard them as functions. Do we have a rule for the product of 2 functions? No, we don't. Well, not yet, right? So what we're going to have to do is we're going to have to get rid of the product. Is there a way for us to get rid of the product? Yes, there is. And how do we do that? We simply multiply. So let's rewrite g of x. That's what we aim to do in here. Okay, so let's rewrite g of x. And so what we're going to do is we're going to use the FOIL method, and we're just going to multiply out. So I've got the square root of x multiplied to the square root of x. And what does that equal to? The square root of x times itself is x, okay? Because that is simply x to the power, and I hope you remember this. This is x to the power half. So if I had to multiply x to the power half to x to the power half, we're going to add the exponent. Half plus a half is 1, and therefore we get x to the power 1, which is simply x. Did everybody follow that? All right, and then if I continue, then I've got okay, let's go negative root x plus 3 root x and negative 3. All right, so I hope everyone's following in there. Wonderful. So let's simplify. So this is simply x plus 2 root x. But as I had pointed out, root x is just x raised to the power half, isn't that so? So I'm going to write that down as x raised to the power half minus 3. Are we all happy with what I have done to simplify in here? Wonderful. Okay, and so it was quite deliberate why I wanted to rewrite the radical, the surd, as a power, because we have a power rule. So that now puts us in a really good situation to compute the derivative. So what is the derivative of x with respect to x? It is simply, waiting for some answers. So utilize your power rule. So you can think of that there as the 1. So what is the derivative of x? Wonderful. Seeing the answers in the chat box, we simply get 1. What is the derivative of 2 times x raised to the power half? So remember, this is technically a constant times a function. We've seen what happens. This is just going to be the constant times the derivative of the function. What is the derivative of x raised to the power half? It is a half times x raised to the power negative half. And then what is the derivative of minus 3? This is 0. Okay, so you could say minus 0 plus 0, put it in there or leave it out, like what I've done. So essentially, what rules have we utilized in here to compute the derivative of g? We have used the sum and difference rule, as you can see, because we've got a function added to a function minus a function. We used the constant times a function rule, and we used our power rule. We've essentially been using all of the rules because we also use the derivative of a constant. All 4 rules were utilized in this problem. Okay, and so that's the beauty of it, being able to see how everything unfolds in the problem and how you are able to apply it. So in here, I can simplify. This is 1 plus 2 times a half is going to give me a value of 1. So that's x raised to the power negative half. But I don't like to write things in the negative exponent. Right, so typically in mathematics, your final answer should be written in the positive exponent. And last week we had seen that we could rewrite negative exponent as positive exponent. So utilizing this rule, we see that we can rewrite it as 1 plus 1 over x raised to the power positive half. And so that would be the final answer. I'm now going to check the chat box. Wonderful, everyone, for putting down the answers in the chat box. Okay, brilliant. So I'm liking the participation. So that was a wrap up of that bit. So now what we're going to do is we're going to talk about how to draw cubic functions and utilize your calculus techniques that we have just learned to answer certain questions. So let's start a section on cubic functions. Okay, so have you covered cubic functions in class yet, or will this be the first time that you're going to be learning about it? Just waiting in the chat box. Ah, perfect. So we've got some responses. Some of you have started it, some of you have not started it, and some of you have already covered it. Okay, so we've got a mix, but let's take a look, right? So a cubic function has the form f of x equals to ax cubed plus bx squared plus cx plus d. So as you can see, the highest power of the variable in here is 3, hence the name cube, right? So this is a cubic function. Now you have studied linear functions before. Y equals to mx plus c is linear. You've also looked at quadratic functions, which was x raised to the power 2, and you had looked at parabolas. So we've looked at straight lines, we've looked at parabolas, and now we're going 1 power higher, and we're talking cubic. And we're going to utilize the calculus that we have learned to understand how to draw cubic functions and understand their shape and their properties. That's the aim here. Okay, so just like when you had learned about the parabola, the coefficient of the first variable, right, of the x cubed, sorry, the coefficient of your x squared in the parabola actually gave you an indication of what could I say? Could I call it the shape? Well, yes, let's call it the shape of the parabola, whether your parabola was going to have this happy face or it was going to have a sad face, right? So likewise, in here, this coefficient of the x cubed, so the a in here, will also indicate to us what type of shape we're going to encounter. Okay, now before I tell you more about what this a is going to help us do, what I want to explain to you is the notion of stationary points. Okay. So to understand stationary points, I want you to recall, what did f prime of x represent? Remember, f prime of x actually represents, this was the slope or the gradient of f of x, of the function, right? F of x at a point x equals 2. So for example, if this was a, so if I said f prime at a, then it would be the gradient of the function f at x equals to a. So that's what this f prime is doing, okay? And we know a few things about gradient, isn't that so? Right, so let's see. More responses about everything. Okay, wonderful. Right, so gradient, with respect to gradient, right? We know that if that is the line, it's a positive gradient and the line rises. So that's a positive gradient. If the gradient was negative, then the line falls in that direction. And of course, gradient equal to 0 is a horizontal line. We all remember that. So this f prime at a specific point x equals to a is indicating to us the behavior of f of x at that point, whether it's on a rise, it's on a fall, or if it's going to be horizontal. So what stationary points do is we essentially, right, so I just wanted to highlight stationary points because that's what we're discussing. What the stationary point does is it analyzes at what point will f of x have a sort of horizontal shape. When does it become flat? Meaning, at what x value is f prime equal to 0? That's what a stationary point is. So we want to find x such that f prime of x equals to 0. And so if f prime of x represents the gradient, it simply means that the gradient is 0. And so it means that the function f is approaching a sort of a flat line. And so when does that typically happen? This typically happens when the line is about to turn in a certain way. So maybe you have a flat line happening like that. So it's flat there. Or you could encounter something like that because it's flat there. Sometimes you encounter this because it's flat there. And so there's all sorts of ways that we could encounter some type of flatness in the function f that we may encounter. So those are just some illustrations. Right, so when you find the x such that f prime of x is 0, we call that x a stationary point. Okay, so let's make a note. This x with its y value, of course, the coordinate, right? So this x comma f of x. So you would have found the x, you can plug it back into the original function, get out the y value, is called a stationary point. A function could have more than one stationary point. Okay, it can also have no stationary point. That's it. And so one of the things that we will have to look at is finding stationary points. Another word that you possibly would have encountered in class is possibly a turning point. Okay, so I'll make a note, turning point. And why would I say such a thing? Because let's go back to an example that we're all familiar with, right? So let's consider the parabola, right? So this would be the parabola, y equals to x squared. Right, so let's suppose we've got y equals to x squared in there. So then observe that we have here at the turning point, the gradient of the tangent line to that turning point is 0. Isn't that so? Wouldn't you say that? If I drew a tangent line to the turning point here, let me do that again. That line is horizontal. Okay, it is flat. And so we see that the gradient of the tangent line at the turning point is 0. Do we all see that? Okay. So far, is everybody understanding this concept of a stationary point? Right, so I've just given you an example that a stationary point is a turning point on the parabola. Okay, because at that point we see that the gradient is 0, because a stationary point is characterized by the gradient being 0. Okay, so that's one thing for us to note. So on a quadratic graph, we have encountered one turning point. A parabola has one turning point. And now we're talking about cubic graphs. That's the point of today's lesson. And so we're still going to have turning points when we talk about cubic graphs. So as I said when I started off, I was trying to give you a description of what this a in front of the x cubed actually does. So if a is positive, then we have a local, more terminology. Another word that I was just about to use for stationary point was a local max. Or you will see we might talk about a min. So in this case, this turning point was the minimum value on the parabola. So we would refer to it as a local minimum. Okay. Local, because this is happening in a neighborhood around the turning point x value. It's happening only in that region close to that value, right? So I don't want to use terminology, but I just wanted to give you an idea of why we're saying local, all right? So it's a local minimum because that turning point was the minimum sort of y value in that region. Okay, so that was more terminology in there. So if we were talking about a local maximum, which was not drawn here, then of course that would be the turning point, and this coordinate would be called the local max. All right. So whenever we have that the a is positive, then this is the shape that you would encounter for your cubic graph. We would have a local maximum followed by a local minimum. And whenever it is negative, then we would have a local minimum followed by a local maximum. And so this is the basic shape that you would encounter. Is everybody following up to this point? Ah, wonderful. Lots of yeses coming through. Okay, so that is why I needed to explain this point or this notion of stationary points. Oh, my video is off. Of stationary points too. So in this case, you see at this turning point, a stationary point, the gradient is 0. Similarly here, the gradient of the tangent line to these points are all 0. Okay, and so we've got that happening. So that's one of the things that we would like to do. So stationary points are analyzing when is the gradient of the tangent line to that function equal to 0, meaning when is that line horizontal? When is it flat? When is no change occurring? That's what's happening, right? And then the other notion that we have to go through and understand is a notion of concavity. Okay, so what I'm going to do is I am going to go back to the parabola, since this is something that we all understand. So before I do that, I just want to quickly check our chat box again. Okay, so we have a question. What would happen if A equals to 0? That's a nice question, Kayla. So if A equals to 0, let's go back to the problem. Right, so if I had to put in a 0 here, so then that becomes 0x cubed, and 0x cubed is 0. So that whole thing disappears. The cubic component from the function disappears. And what will you be left with? What will you be left with? You'll be left with a quadratic. Okay. Yes. And so you will end up drawing a parabola. Wonderful. So I see you followed that point well. Okay. So let me remove that. Let's go back. So that was stationary points. So slowly what's going to happen is this is all going to lead to us eventually drawing a cubic function for ourselves, but I'm building on all of the theory that you need to know, right? So the second bit of the theory that we need to cover is concavity. Sorry, poor spelling. Right, concavity. Okay. And so once again, it's always good to remind yourself, what does the derivative do? Remember, f prime is representing the gradient of the function at a point, or the gradient of the tangent line to the graph at that point. That's what it's doing. So I want you to keep this notion of gradient at the forefront of everything that you're thinking about right now. And what we're going to do is we're just going to kind of do this little case study together where we analyze, and I want you to answer me. I'm going to ask quite a bit of questions now about what is happening on for the following lines that I'm about to draw. Okay, so let's say I drew this line that's quite steep. Let's say this one had a gradient of, I'm just making up random things now. Okay, well, not random, but I'm just making up some numbers here. So let's say this gradient was 9, and then there's another line here. Let's say this gradient for this line. So would you expect the gradient of this line to be bigger than 9 or smaller than 9? So the first line, this one's quite steep, and then this line is considerably flatter than the one with gradient equals to 9. So if it's flatter, would you expect the gradient to be bigger than 9 or smaller? Smaller, wonderful. We've got the answer smaller because it's less steep. Great. Right, so let's just say that one was 5, okay? I'm just saying it's 5. And then here. Okay, so that's what I've got. This one's flatter. So maybe this is like, let's just say it's 0. Let's pretend it was a horizontal line, okay? Gradient equals to 0. And now I've got this happening. What's happening with the gradient here? Positive, negative, what's going on? Negative, great, we've got answers, it's a negative gradient. And then, okay, so it's negative, but I'll put it down as negative 4, right? And then look at this one. Is this one negative or positive? Still negative, great. But is it more negative than the previous line? So how negative is it going to be? Is it going to be bigger or is it going to be smaller than negative 4? Very negative, wonderful. Right, so maybe I'll just put in negative 10 or something like that. Right, so what's happened? Look at the numbers that we've got here, right? And let's work from left to right. So I'm going in this direction, right? So observe what's happened when we start from here and we proceed in that direction. The gradient is getting smaller, isn't that so? 9 drops to 5. 5 drops to 0. 0 drops to -4. And -4 dropped to -10. Do you see what's happened? It got more negative. Right, wonderful. I see the chat box. Right, so as we go from here to here, we got more negative. We got smaller. That's what happened. Yeah, poor choice of words there. Let's just say smaller. So the gradient decreased, right? And so this pattern that we've just seen, well, not really a pattern, but this relationship that I've just explained to you in here, we see the gradient decreased. And what is the shape here? So these straight lines could be the tangent lines to the graph, and this would have been the graph. Okay, so this would have been the graph. Okay, so mind my shape, but imagine it was perfect, right? So this is called concave down. Right? So whenever you have that the gradient is decreasing from left to right, we regard this as a concave down shape. Okay, so that's what's happening. So even if you've got half of the diagram, so whether you have this, or whether you have this, or whether you have this, all of these things are concave down. Do we all understand what I've just explained using this illustrations? Would you be able to kind of pick out concave down from a picture? Okay, great. So what I'm trying to show you is that you could identify it using these pictures that I've put here, but also if you don't know how to identify it, you can quickly just do a mental calculation. Is the gradient decreasing from left to right? As the X value increases, is the gradient decreasing? And if it is, because it's decreasing on this, it's decreasing on this, and it's decreasing on this, concave down. And so that's how you find out when something is concave down. So likewise, let's go through this exercise. Let's talk concave up. Of course, analogously, it's going to be doing the opposite, right? So, so let's say I gave you that. So gradient, is it negative or positive for this line? Negative, wonderful. Right, so I'm just going to say it's -9, right? And then here, it's still negative, the line is still falling, but it's much flatter, right? So if it's flatter, then the gradient should increase. And so it would be, I'll say -4. And then let's just say we've got here gradient 0, it became very flat. And then now it starts to go on to a rise, right? So this is now positive. So I'm just going to say, let's say it's 3. And then it gets steeper, right? Still positive, but now steeper. So the gradient has increased significantly. So let's say 8. Okay, now it's steeper than the other line. I'm just going to say 10. Right, so my numbers are in there. So again, now what has happened as we go from left to right? The same protocol we followed. As I go this way, what is happening? Can you see the gradient is increasing from -9, it becomes -4, then 0, then 3, then 10. So here we see the gradient is increasing. And so whenever you have that your gradient is increasing, we call this concave up, okay? And so, of course, these straight lines were representing tangent lines to the curve. So if I had to draw a curve, then it would be, you know, something like that with these lines touching it. And so that's your concave up sort of shape, a generic shape that you would encounter. So that is concave up. So even if you see portions of this concave up shape, if you had to see, for example, this that is still concave up. If we saw this, that is still concave up. So as long as you see that the gradient is increasing on the curve, it is increasing on this curve as we can see, then we call that concave up. Wonderful. Is everybody happy with what we've just gone through? Okay, so everything that I've explained here is about the gradient. It is about the increase or the decrease in the gradient, okay? But before, we looked at the increase or the decrease on a curve in general. So because I'm looking at the increase or the decrease, the rise or the fall of the gradient, this means that I need to find the gradient of the gradient. Do you kind of make that connection that I now need to talk about that when I'm talking about rise and fall of the gradient, not rise and fall of the line, that I must now therefore take the derivative of the derivative. And so if I want to talk about concavity, f double prime, right? So we then have to talk about the derivative of the gradient, which is the derivative of f prime. And so whenever f prime of x is positive, we call this concave up. Okay, so if f prime of x is positive, then it is concave up for x, right? So typically concave up for x, where x is on some interval, right? So you would be able to see for which x values the function is concave up. And when the gradient, the derivative of the gradient, meaning the second derivative of f, is negative, then we regard this as concave down. Okay, let's look at our chat box. I see there's quite a few comments. How would we identify? Yes, so here we go. Just answered the question. Wonderful. Great. Right, so you calculate your second derivative. How do you calculate a second derivative? You first calculate the first derivative, and then you calculate the derivative again. So just differentiate twice. And then you look at the function, and you'd be able to see when is this positive and when is this negative. Okay, and then for all those x values where the second derivative is positive, we call it concave up on that interval. And whenever the second derivative is negative, for all those x values on that interval, it'll be concave down. Okay, now the other thing that we like to typically analyze is when will so this is positive and negative, but I haven't spoken about what happens when it's zero, right? So again, as usual, when the derivative is equal to zero, so here this is a second derivative equal to zero, but earlier when we had the derivative equal to zero, what happened? It was a stationary point, right? So now here, again, what it's going to signify, because it was previously a change in rise and fall, now it's going to be a change in concavity. So whenever the second derivative is equal to zero, we then say that this signifies a change in concavity. So meaning the function is probably changing from concave up to concave down, or concave down to concave up. So if this here is concave up, and suddenly the function changes to concave down, so there would be some point in here where f double prime of x equals zero, right? So I hope that we followed that graphical explanation. So someone said that they don't understand. Okay, so up to this point, do we understand this definition that I've just given? That when the second derivative is positive, it's concave up, or that for all x values on this specific interval, right? It's concave up for this x. And when the second derivative is negative, then it is concave down for that x value for which it is satisfied. Are we okay up to that point? Okay, so you've said no. So are we following up to this point then? Let's figure out where did things go wrong and let's try and correct this. So do we understand the notion of concave down? Concave down represents the following property, that the gradient is decreasing. Do we understand that? Wonderful. All right, so so we've got concave down, gradient decreases. So remember, right? And then we've got concave up, gradient increases, right? So I'd like for you to kind of see this relationship happening. So previously we had the gradient rises, right? Sorry, the line rises and the line falls. So when the line rised, we had positive gradient. And when the line falls, we had negative gradient. And now we're saying that we're not talking about the line, we're talking about the gradient itself. So now gradient increases, gradient decreases. So when the gradient is increasing, concave up, gradient decreasing, concave down. Okay, so the gradient is represented by f prime as we had learned, isn't that so? F prime represented the gradient of the function at a specific point at that x value. Are we following up to that point? Great, wonderful. But now I want to know about when is the gradient increasing, right? And typically gradient tells you about increase and decrease, right? Because that's what gradient does. So I now need to find a gradient essentially of this gradient, right? So, and from our understanding, so this is like a very basic explanation to get you to understand this, right? So we need to find the second derivative to analyze when will the gradient increase. And so this is the gradient of a gradient. And when will the gradient increase? When it is greater than 0. When does it decrease? When it is less than 0. So that is why we've got the second derivative. Greater than 0 represents concave up, and the second derivative less than 0 is representing concave down, right? And so is that okay now? Right, so okay, so I see you've got a yes, and then we've got another question. When we derive twice, does it mean we're going to end up with a straight line? And how do we recognize concavity on a straight line? So remember, we're not, so when we derive, you may end up with a straight line, isn't that so? It's possible, depending on the function you're given. Well, if I gave you, for example, f of x equals to, oops, x to the power 5, then when you derive twice, you're not going to end up with a straight line. Okay, you're going to end up with a cubic function in there. So it's not always the case. But to answer your question, you asked, how do I use a straight line to talk about concavity? So you don't, right? You use the original function to analyze the concavity, but we use the second derivative to determine the points where the original function is concave up and concave down, and where the original function has a change in concavity. So we use the second derivative as a tool to analyze the behavior and the properties of the original function. We're not going to use, for example, as you gave an example, a straight line to analyze the cubic function. Okay, right. So coming back to Shegofatso's other question. So, all right, so then I think this is the last bit that I now have to explain, and that is the change in concavity is determined by finding x values when the second derivative is equal to 0. So here we see when it's positive, we've got concave up. When it's negative, we've got concave down. And so when it's 0, something else must be happening. And so that's indicating to us this change. So previously, derivative equal to 0 was a stationary point. Now the derivative of the derivative, when that equals to 0, we've got a change in concavity. Are we all happy up to this point? So what I'd like to do now is I'd like to look at a question. Okay, so let's do that. Okay, right. So continuing with that same paper, here is a nice question. Question 9, we're given a function, 2x cubed plus 3x squared minus 12x. It's sketched below. So as you can see, the coefficient of the x cubed is 2, and it is exactly as I had explained. You first have the maximum and then followed by the minimum. So that's happened in the shape, right? And then they say A and B represent turning points. So we have a turning point at A and we have a turning point at B. Observe that based on the terminology we had learned, this turning point at A is a local maximum, right? It's a max in that region. And this turning point at B is a local minimum. So maybe let me just make a note. Local max and local min. Okay, that's what we've got. The question says, determine the coordinates of A and B. How do you think we're going to go about doing this? So we know that A and B are turning points. Do we know anything special about them with respect to the properties that we've learned? What have we learned? We've learned that at a turning point, the tangent line, the slope of the tangent line at a turning point is 0. Isn't that so? And so that's what we have happening here. So the slope of the tangent lines to these points are both 0. Exactly. So as per the chat box, we see that it's stationary points. And how do we solve for stationary points? We need to find x such that f prime of x equals 0. So let's do that. Okay, so let's answer. So we've got f of x, I think it was f of x. Yes, 2x cubed okay, so I'm just going to quickly copy this. Great. Okay, so this is our function. Now we need to find f prime of x. So let's differentiate using all of our basic rules. So using our basic rules, what is the derivative of 2x cubed? It is 6x squared. What is the derivative of 3x squared? So I'm using my sum and difference rule as well. As you can see, there's a function being added to a function, and then we've got another function being subtracted. Okay, so I'm using that rule. So I'm now adding it to the derivative of 3x squared, which is 6x, and then subtract the derivative of 12x, which is 12. I hope everybody's happy with that calculation. Wonderful. And as per the chat box, our derivative must be equated to 0, and we must solve for x. So I want f prime of x equals to 0. So that means we are solving 6x squared plus 6x minus 12 equals to 0. So I see that I can factor out positive 6. So I'm left with x squared plus x minus 12. Oh, sorry, minus 2. Minus 2. Okay. And then what we can do is we can further factorize this. So I can write down 2 factors. And so I see that I would write down x plus 2 in here and x minus 1. Are we all happy with this? Just waiting for some feedback so I know whether we can proceed. Do we wait? All good. Perfect. Right, so let's read off the solutions. What x values do we get? So we have x equals to -2, x equals to +1. So we've got 2 candidates for stationary points, and we now need to find the corresponding y value. So to find the coordinate, we take this x and we plug it into the original function, okay? So I need to find x comma f of x for each of these x values that we've got. So the first one would be -2 comma f at -2. That's what I need. And the second coordinate is +1 comma f at +1. Okay, so what is that going to be? Let's plug in -2 into the original function. Right, where's the original function? There it is here. So if I plug it in here, plug in -2, so that gives me -16 plus 12 minus 24. Do we get +20? Please verify. So I've got -2 comma 20. And then the last one, I need to know what is the y value. Plug in 1, 2, 3, minus 12. So it's -7. Let's check the chat box. Wonderful. Everybody said yes. Great. And so we have got these 2 coordinates for the turning points, but which one is A and which one is B? So one of them is the x value is -2 and the other is +1. Let's go to the picture. The picture will be helpful. So we've got a -2 and a +1. So clearly this must be negative. Oops, what's happened? This must be -2 because we've got a negative x value, and this must be +1. Okay, so we've got A and we've got B. Let me label them appropriately down here. So this one is A. Oh, I don't know why this is happening. Here we go. This one's A and this one's B. Wonderful. Let me check the chat box again. Okay, wonderful. All right, so that's what we've got. And then let's see if we've answered the question. Yes, we have. So we'll determine the coordinates of A and B. And then it says, for which values of x will f be concave up? So we now need to determine when is this function concave up. But I can already kind of see where this function is concave up based on what we've learned, isn't that so? So I can see concave up is taking place along this region here. Along here. This is all concave up. That's what concave up does. And of course, possibly here, but at some point here, it's going to change. So this was concave down, and then it's going to change to concave up. So I need to determine at what point here is it changing to concave up. So the first thing we need to do is we have to determine where the change occurs, right? So we know this is concave up. So let's determine where does the change in concavity occur. Or what we could simply do is we could analyze the second derivative, right? So we're looking at the second part of the question. So the second part on concavity. Okay, so I see that our time is limited. We have gone over time, but let's finish this bit of the question and then we could end. Right, so we've got f prime of x is equal to, let's quickly remind ourselves, it's equals to 6x squared plus 6x minus 12. And then we need the second derivative. So we compute the derivative of the derivative in here. And so we see that that's going to be 12x plus 6. Are we all happy with that? Right? And so now we want to determine when is it concave up? What is our definition for concave up? Concave up was when f double prime of x is greater than 0. So that's what we need to do. I need to find out what are the x values for which this is greater than 0. So that says 12x greater than negative 6. And so if I divide both sides by 12, the inequality remains the same, right? It's still the same. And it becomes negative 6 over 12, which equals to minus a half. And so we see that it is concave up for all x greater than negative half. So if we go back to our picture, that means the x value on here where the change in concavity occurs would be at negative half. And so it's concave up for all x bigger than negative half. And so that is where I'm going to end today. You could quickly copy down the last bit of the question to attempt on your own. And it says, determine the equation of the tangent to f at the point 2, 4, where if you look at the picture, that is the coordinate 2, 4. So we want the equation of the tangent to this point. So I hope that you all followed the lesson and you did enjoy learning about stationary points, concavity, and some basics to cubic functions. As I mentioned at the beginning of the lesson, we will announce when the next set of lessons will be taking place. We plan to host a winter school on Zoom. So this video will be posted on YouTube. So you could just follow the NETEX channel on YouTube to get updates on the new videos. And of course, I'll be seeing you soon at the upcoming lessons. So thank you all for joining. Thank you and goodbye.